Now, since these guys are acting like vectors, SZ has to act like a matrix. But, what matrix could possibly give us this? Of course, that all depends on the values of L and M. Now, I said spin a half is the simplest because it gives only two possible states. Spin up is the state half-half, and spin down is the state half minus half. And so, these two spins are going to make up the state of every single spin half particle. Now, what happens when we plug them into something like this? Well, we finally get a way to figure out what the matrix that satisfies this equation is. Now, this one in particular is pretty simple. Do you guys remember how to solve for the matrix? Because I don't. Not just kidding. Let's do it the old-fashioned way. Just taking, since we're doing 2x2 matrices, this method is fairly simple. Although you can also do the method where you take the determinant to both sides. So you get half h bar, half-half. And of course, since you're multiplying this way, you get that the first element of the new vector formed is half a plus half b, and the second element of the new vector formed is half c plus half, half c plus half d. And so that's going to be equal to half h bar over and half h bar, which means that things are going to get a little bit trickier because you now get that a plus b has to be equal to half h bar, and c plus d also has to be equal to half h bar, which means that this matrix could be anything. Same thing with s squared. Well, there's no point in putting the magnitude signs at this point. So s squared half-half is going to be equal to L, well, in this case, half 1 plus a half multiplied by half-half. Sorry, h bar squared, half-half. And what you're going to see here is another matrix multiplied by a vector is equal to 3/4 h bar squared multiplied by the same vector, which means that you have to solve for these values again. One more thing that you have to note. Spin up is going to give us nice tidy values of the SZ and S squared matrices that have totally real elements, but spin down means we're not going to be as lucky. You see, if we work with spin down instead, what happens here? Well, we get ABCD multiplied by half minus half is equal to what? Half A minus half B, and half C minus half D multiplied by half minus half is equal to half minus half h bar multiplied by LM, which is half minus half. And so when you aim to do this as well, you get stuck in another trap because you get, well, A over 2 minus B over 2, A minus B, to simplify things a little bit, is equal to minus 2 h bar times a half, which becomes minus h bar. And c over 2 minus d over 2 minus a half is equal to what? Oh, sorry. We get c over 2. Wait, why'd I leave? No, why'd I leave this vector here? That makes absolutely zero sense. C over 2 minus d over 2, or c minus d, is equal to, oh yeah, that explains why I made a mistake. Oops. So we get that a minus b is equal to minus h bar over 2, as opposed to positive h bar over 2 and positive h bar over 2 here. And the same way, c minus d is equal to minus h bar. No, why am I doing this? C minus d is equal to h bar over 2. Which means something pretty significant, because if c plus d is equal to h bar over 2, and c minus d is equal to h bar over 2, that kind of makes it sound like d is equal to 0, and c is equal to h bar over 2. And, well, we don't get the same luxury with, oh, wait a minute, if we add up these two equations, it gives us the luxury that a is equal to 0, and b is equal to minus h bar over 2. Yeah, that seems awfully simple. Which means that for these cases, we get 0, h bar over 2, h bar over 2, 0, or factoring out the h bar over 2, 0, 1, 1, 0, which I'm pretty sure is the the identity matrix is not changed by the transpose. So let's just call it the reverse identity matrix or something. I don't know. This is one of the commonly known Pauli spin matrices, and this thing is one of the most important constructs in spin theory. Now, spin is